All right, let's talk about oxidation number. Oxidation number is essentially the charge on the metal, non-metal, transition metal, whatever species that we're looking at. Now, the oxidation number is determined by what's around it. Okay, so there is two different methods that we can use. We can use the Lewis structure method, or we can use the algebraic method. Okay, most often students do like the algebraic method. Okay, Lewis structure, you gotta have, it's very visual. Let's put it that way. It's very visual. But I'm gonna show you both ways and how we can break this down and then move forward. So let's say, for example, I have H2SO4. Okay, H2SO4. This is also known as sulfuric acid. All right, this is also known as sulfuric acid. So to do the algebraic method, in order to figure this out, what we need to do is this. We need to define what we're looking for. A good trend and what we tend to look for is that sulfur, in this case, is the central atom. The central atom is the main atom that we're looking at as far as oxidation number or oxidation state. So if this is what we're looking for, we're going to put the variable x in its place. So in order to do that, we put a variable x here. Here, each other portion is going to represent the number of atoms as well as its charge. So we want to do 2 times plus 1. The normal charge associated with hydrogen in this case is plus 1. Okay, plus x. Okay, plus we have 4 oxygens. So this is going to be 4 times -2 equals the overall charge. There is no overall charge, so it's equal to 0. When we solve for this, x should be equal to plus 6. Okay, so the oxidation number, or oxidation state of sulfur in this case is plus 6. If we look at the Lewis structure method, we can break it down as far as sulfuric acid. I'm opting out the long pair, so don't get too distracted by that. So we would say sulfuric acid is this. Obviously, we have long pairs there, all around us. But if we look at the different bonding around us, we have 2 bonds here, which in this case to be -2 is be -1, -2, and -1. That's it around this. Each bond represents essentially a negative charge. Negative charges tend to reside on the most electronegative atom. Okay, it stabilizes much further than something that's not as much electronegative. Let's look at another case. Look at dichromate. Okay, if I want to still figure out what Cr is, what I want to do is 2x plus 7 times -2 equals -2. X should be equal to plus 6. Now, when you're looking at this, this means that each chromium is plus 6. Okay, you want to keep that in mind. Let's try another one. Now keep in mind this algebraic method, it counts for most things that you can go through, but the Lewis structure method usually can help you out anytime. But the algebraic method, the exceptions would be, say, for example, hydrogen peroxide or sodium hydride or calcium hydride. Those can be some exceptions that you can't really use this method on. But we'll look at some other ways and some other possibilities along the way. So we do MnO4. This is permanganate. Okay, so this is permanganate. All right, we're going to look at permanganate. It's usually potassium permanganate, but we're not going to put the K for now. Or we can look at MnO2. Okay, it's usually said, they'll say manganese dioxide. What it really is manganese 4 oxide, because if you look at it, which we'll talk about that a little bit later. All right, so when we're looking at this, we can break it down. This is going to be X plus we have 4 oxygens times -2, which is equal to -1. This should give me plus 7. Here, x, so it's x plus 2 times -2, which is equal to 0. X should give me plus 4. Okay, so this gives me a lot of stuff that I really need to know about. Okay, this is how I can calculate the oxidation number. We can look at a reaction scheme such as CH4. All right, or rather not a scheme, we're going to get to that. We're going to look at CH4. Same thing, okay? This represents X plus 4 times plus 1 equals 0. X equal to -4. We can do something like CO2, which that's the scheme we're going to be talking about pretty soon. We have X plus 2 times negative 2 equals 0, which X is equal to plus 4. Now, if we look at a reaction, when we're dealing with oxidation and reduction, this is where this really plays a huge part. So let's say, for example, I have CH4 plus O2 goes to CO2 plus water, which we can balance as such. When we're trying to figure this out, anything in this elemental state or in this natural state, oxidation number is 0. Okay, you want to remember that its natural state or elemental state is 0. Okay, so when we're looking at CH4, we can also apply the method. We already figured out this is plus 4 and this is this is actually negative 4. This is negative 4, and this is plus 4. So this underwent oxidation. Okay, this underwent oxidation. All right. The more positive something becomes, the more likely that you can see that it's undergoing oxidation. And we're going to talk about oxidizing agent versus reducing agent and so forth. A better example even than this that I like to have, and this is 0, oxidation number is 0, remember, for elemental states. We can do something like Fe solid. Remember, I'm not including any states. All these are gaseous except for that one. Plus O2, which is gas here. We do Fe2O3. This is, we'll figure out what the name of this is in just a little bit. But basically 2 here, 4 here, and then we have a 3 here. Okay, so this is the rusting process. So this is rusting process. Okay. All right, so this is the rusting process. Iron becoming basically iron 3 oxide, which we'll look at how we can do that too. And also figure out what its oxidation number is. So we know that in this elemental state, for metals, they tend to be solids. So if you see something like solid and it's by itself, then you essentially can probably say that it's going to be oxidation number of 0 and 0 here. Okay, so as iron goes to this is actually iron 3 oxide. All right. Now we can figure out this overall state by putting the 2 here. We can say 2x plus 3 times negative 2 is equal to 0. X should be equal to plus 3. Okay, so it's going 0 to plus 3. This process is oxidation. This process is going to be, okay, reduction. Gain of electrons. Oxidation is loss, reduction is gain. We can remember this by using oil rig. Oxidation is loss, reduction is gain. Okay. So how do we figure out oxidizing agent and the reducing agent? Well, the oxidizing agent undergoes reduction and the reducing agent undergoes oxidation. So due to the fact that this is undergoing oxidation, we can say this is the reducing and this is the oxidizing agent. Okay, so it went from 0 to plus 3. This one was 0 to essentially negative 2. It underwent reduction. Okay, good rule of thumb that you want to remember: the higher oxidizing agent, oxidizing state or oxidation number rather. The higher oxidation number, the better the oxidizing agent. That's what I was trying to get at. Okay, so that's what you want to really look for when you're trying to solve these problems. Once you have this, then you can solve ionic equations. You can start balancing those equations and so forth.